They're one of the most mysterious objects in the universe, but black holes may not be what you think they are. Here's a quick black holes explained. To understand what black holes are, we first have to understand what they're not. Black holes aren't actually black, and they don't have a specific size or shape. Instead, black holes are regions of space with extremely strong gravitational pull from which nothing can escape. This is known as the event horizon. Anything that crosses the event horizon cannot get out, not even light, which is why it appears black. While this is a visually striking image, it's not entirely accurate. In reality, light doesn't bend around a black hole. Quasars are extremely luminous and compact, making them among the most powerful energy sources in the cosmos. By studying quasars, astronomers can explore the behavior of matter under extreme conditions and probe the physics of the early universe. As I mentioned earlier, there are two main types, stellar and supermassive. Stellar black holes are the smaller of the two and form when a single star collapses. These typically range from a few to several dozen times the mass of our Sun. They believe that either black holes do unexist at all, or that they exist but are not as massive as astronomers believe, while we may never be able to observe them directly. Their effects on other objects in the universe provide us with valuable insights into the nature of gravity, space, and time. Supermassive black holes are thought to grow by consuming gas and dust from their host galaxies. I also encourage you to subscribe so you don't miss out on future videos. Thanks again for watching, and I'll see you next time. As they consume these materials, they release huge amounts of energy in the form of radiation. This radiation can travel to other galaxies and potentially be absorbed by other supermassive black holes, which would cause them to grow faster. This process could theoretically allow black holes to communicate with each other and share information about their environments. While this is still just a hypothesis, it is an exciting possibility that could revolutionize our understanding of black holes and the universe as a whole. Who knows? Maybe one day we'll discover that black holes aren't just mysterious and dangerous objects, but are actually key players in the vast cosmic network that connects everything in the universe. So keep looking up at the night sky, and who knows, maybe one day you'll be the one to make the next groundbreaking discovery about these enigmatic cosmic wonders. Black holes are one of the most mysterious objects in the universe, but recent observations suggest that they may not be quite what we think they are. Some astronomers now believe that black holes may actually be able to communicate with each other, and that they do this by emitting a type of radiation known as Hawking radiation. Hawking radiation was first predicted in 1974 by Stephen Hawking. He suggested that black holes are entirely black and that they emit a faint glow due to quantum effects near the event horizon. This radiation has never been detected, but if it could be observed, it would provide strong evidence for the existence of black holes. Recent observations of gamma-ray bursts have led some astronomers to believe that black holes may be communicating with each other through Hawking radiation. Gamma-ray bursts are some of the most powerful explosions in the universe, and while their exact cause is unknown, they are thought to occur during the formation of black holes. If black holes are emitting Hawking radiation during their formation, it could explain why gamma-ray bursts are so powerful. This is just one of several new observations that suggest black holes may not be as solitary as we once thought. In fact, some astronomers now believe that black holes may form networks that allow them to communicate with each other and possibly even share information about their surroundings.
Yes.
These people often cite the lack of direct evidence for black holes as proof that they do exist. However, this argument is flawed because it ignores the indirect evidence that we have for black holes. On the other hand, supermassive black holes are truly enormous, with masses that can reach millions or even billions of times the mass of our Sun. These giants reside at the centers of most galaxies, including our own Milky Way, instead. The apparent bending is a result of the intense gravity stretching and distorting the light waves themselves. Unfortunately, if you were to fall into a black hole, there's no doubt that you would be met with an extremely unpleasant fate. As you approach the event horizon, the gravity would become incredibly strong, stretching and crushing your body in a process known as spaghettification. Spaghettification occurs due to the extreme tidal forces near a black hole. These forces stretch and distort objects, making them thinner in the middle and thicker at the ends, kind of like spaghetti. Once you cross the event horizon, you're met with a strange and terrifying sight. The intense gravity distorts everything around you, making it appear as though you're surrounded by a thick fog. As you continue to fall, the darkness becomes complete, and all sense of time disappears. Eventually, you're pulled towards the center of the black hole, where everything is destroyed and nothing can escape. This phenomenon, known as gravitational lensing, can actually help us detect black holes indirectly by observing the way they affect light from distant sources. There's a lot of evidence for black holes, but the most compelling is probably the observation of stars orbiting around them. When a star orbits a black hole, it speeds up as it approaches the event horizon and slows down as it moves away. This change in speed can be measured by observing the star's light, which changes in wavelength as it approaches and moves away from us. By studying these changes, astronomers can infer the presence of a black hole. Another piece of evidence for black holes comes from gravitational lensing. When light passes by a massive object, it can be bent and distorted by the object's gravity, creating a lensing effect. This effect can be used to detect black holes because they are so massive. They can cause light to bend around them, creating a ring-shaped image of objects behind them. The boundary of the event horizon is known as the Schwarzschild radius. Supermassive black holes are found at the centers of most major galaxies, including our own Milky Way, and their influence extends far beyond their immediate surroundings. As the central engine of a galaxy, supermassive black holes regulate star formation. Early civilizations often had myths and legends that described celestial objects that could trap and devour anything that came too close. However, it was until the 17th century that scientists began to develop a more scientific understanding of black holes. As our knowledge of physics and astronomy grew, the concept of the black hole emerged as a natural consequence of Einstein's theories of general relativity. In the early 20th century, scientists like Carl Schwarzschild, David Kipping, and Subramanian Chandrasekhar made significant contributions to our understanding of black holes, laying the foundation for modern black hole research. Today, black holes remain one of the most fascinating and mysterious objects in the universe. As astronomers continue to explore these enigmatic phenomena, they not only unravel the secrets of the cosmos, but also push the boundaries of human knowledge and understanding, and control the distribution of matter within their host galaxies. By studying these galactic giants, astronomers gain insights into the formation and evolution of galaxies over cosmic timescales. And it's important to note that this isn't a physical thing, just the point of no return. Once you cross it, there's no coming back. The reason black holes have such a strong gravitational pull is because of their mass. The more massive an object, the stronger its gravity. When a star is born, it starts off as a cloud of gas and dust that collapses under its own gravity. As it collapses, it heats up and forms a ball of plasma. This is a protostar. If the protostar is massive enough, it will continue to collapse until it forms a black hole. Now, here's where things get interesting. Black holes can't technically be observed directly because, well, they don't emit any light. However, we can observe the effects they have on other objects in their vicinity, such as stars and gas. These typically range from a few to several dozen times the mass of our Sun. At the other end of the spectrum, there are supermassive black holes, which can be millions or even billions of times the mass of our Sun. These giants reside at the center of most galaxies, including our own Milky Way. But how exactly do stars turn into black holes? It all starts with a star's core. As a star ages, its core begins to run out of hydrogen fuel. Without the outward pressure that fusion provides, the core collapses under the force of gravity. For low to medium mass stars like our Sun, this collapse results in a white dwarf. More massive stars, however, face a more dramatic fate. Their cores collapse so intensely that they break through the electron degeneracy pressure. This allows gravity to take hold, crushing the core into an incredibly dense singularity. The boundary around the singularity is the event horizon, marking the point of no return for anything that ventures too close. Even light cannot escape its grasp. The intense gravity near a black hole distorts space and time, creating a deep abyss that sucks in anything that gets too close. And once something crosses the event horizon, it can never come back out. By studying these interactions, astronomers can learn a lot about black holes. For example, by observing how much light is bent around a black hole, scientists can estimate its mass. Black holes also cause space and time to become distorted, creating a sort of ripple effect. This distortion can be detected by measuring changes in the brightness and color of stars near the black hole. These ripples are known as gravitational waves. Black holes come in a range of masses. The smallest ones are known as stellar black holes, which form when a single star collapses. You might have seen the classic depiction of light rays bending around a black hole, giving it a ring-like appearance. But black holes aren't just cosmic vacuum cleaners. They can also play a crucial role in the evolution of galaxies. The immense gravity around a black hole creates an environment where matter can reach incredibly high temperatures, giving rise to some of the brightest objects in the universe, quasars. While black holes may seem like relatively new discoveries in the world of astronomy, the idea of these enigmatic objects has been around for centuries. Let's talk about the different types of black holes now. What happens if you fall into a black hole? So let's talk about the evidence for black holes now. Now, some people still deny the existence of black holes. In conclusion, black holes are truly fascinating objects that continue to captivate scientists and stargazers alike. These new ideas are based on observations of supermassive black holes at the centers of galaxies. Thanks for watching. If you want to learn more about black holes, I recommend checking out some of my other videos on the topic.